matter of interest throughout the sciences. In particular, physicists were among the first to see this as an opportunity to reinvigorate their interest in macroscopic systems, and among that group at the very beginning was Harry Swinney, in which he did some pioneering experiments on the role of chaos in continuum systems, and was responsible for some of the first major discoveries. He's still working on the subject today in many different guises, and he's here to talk to us.
Okay, thank you very much. So let me begin by giving some background. I do experiments, as Dan mentioned, and I was interested in different types of experiments that might be done on fluids in the early 1970s. And read this paper by Landau about the transition to turbulence. As the Reynolds number of a fluid is increased, it will exhibit, in Landau's view, the fluid will exhibit a sequence of bifurcations. Each bifurcation would bring a new frequency into the dynamics. And the successive frequencies would be incommensurate with the existing frequencies. His view was that turbulence was the name for what occurs after you've reached a large Reynolds number, and there are many frequencies present. There are many discrete characteristic frequencies. So I discussed with a colleague, Jerry Golub, possibility of doing an experiment to test Landau's idea. We searched the literature to find experiments where people had measured the discrete frequencies that would appear at successive bifurcations. And despite extensive search, we couldn't find any such experiments. There were a number of experiments on the onset of instability as a fluid Reynolds number was increased. But beyond the primary onset of instability, there were no experimental results that we could find. So we decided to look at a problem that had been studied since early in the 20th century, flow between concentric rotating cylinders, and increase the rotation rate of the cylinders to increase the Reynolds number, and look to see what happens. So the first experiment that studied any instability in a fluid as the Reynolds number was increased was this classic experiment, a real tour de force by G.I. Taylor. And you're probably familiar with the figure. Here we have at the bottom thermodynamic equilibrium, both cylinders. This is the outer cylinder frequency, it's 0. The inner cylinder is also at rest, and you can increase the speed of rotation of the inner cylinder till you get to an instability. So G.I. Taylor first did an experiment in which he could rotate either cylinder, but increasing the inner cylinder speed. The experimental data here are the red dots. And you see, he saw a transition, very well-defined transition. Measured the transition within the Reynolds number with an accuracy of 1% or so. And you can see the additional red points along this line. So this is the instability curve with both cylinders rotating. This is the outer cylinder, lots of red dots here. And he took a photograph of dye that he injected into the annulus between the cylinders, and this is his photograph showing a vortex pair. In one boundary, you have fluid flowing inward. The next boundary above it, you have fluid flowing outward around the vortex, around the donut-shaped vortex. Then he did a linear stability analysis of the Navier-Stokes equations and calculated these green points, and the agreement was remarkable, to 1% or so. That was the first example of the prediction of instability and the corresponding experiment. Now, there have been some giants in the field who had attempted to calculate instability for a situation that would be measured in the laboratory, but they had all failed. This is a quote from Taylor's paper. So we built a system and put flakes in the fluid so we could do visualization and observe this first pattern that formed at a well-defined Reynolds number. Here you see the Taylor vortices. And then we increased the, let's try this. Yeah, increased the Reynolds number and saw bifurcation to wavy vortex flow. And that had been observed earlier by Coles, who studied it pretty extensively, the Taylor vortices. So that brings one characteristic frequency, the frequency of the waves as they pass a point in the fixed laboratory reference frame. And we increased the speed quite a bit more, and we saw, just looking in flow visualization, that the flow became very complicated, whether you call it turbulence or it's a complex non-periodic flow. Or maybe it's a multi-periodic flow in the picture of Landau. So we did an experiment in which to characterize the frequencies, we measured the velocity at a point in the annulus, the radial component of the velocity at a fixed point, and then obtained from that time series of the velocity, long time series of the velocity. And to determine the frequencies present, we decided to compute velocity power spectra. As far as I know, this is the first fluid experiment which determined the temporal frequencies present in a fluid. We looked in the literature and we found no previous experiment. But I had been an engineer at NSA, and all we did was spectral analysis. So it seemed like the natural thing to do. So we computed power spectra, and there you see one with a single frequency component. If you look out to higher frequency, we could see 15 harmonics. Notice the signal to noise is pretty large. The peak intensity here is 5 orders of magnitude above the instrumental noise. And temporal resolution, or spatial frequency resolution, is very good also. That's a very narrow peak. So we increased the Reynolds number. Yeah, okay. Increase the Reynolds number, and you see now we have many frequencies. But if you analyze the spectra, you find that all the frequency components going out to much higher frequencies are multiples, sums and differences of these two, like twice omega-2 minus omega-1, or 3 times, and so forth, right? So there are only 2 fundamental frequencies. And we varied Reynolds number over a range around the Reynolds number at which we saw the second frequency component appear, and looked at the ratio of those frequencies. We were concerned that omega-1 might be rationally related to omega-2, but we could see that the ratio varied continuously, smoothly, as you varied the Reynolds number, ratio of omega-1 to omega-2. So we then increased the Reynolds number some more, looking for the third frequency, having Landau's picture in mind where there would be a new frequency that would be brought into the motion at each successive instability. And we found these 2 frequencies that we had previously, but there was broadband noise, and this was 2 orders of magnitude above the instrumental noise, and it increased as we went up in Reynolds number. We long thought it was instrumental noise from some lack of care in the experiment, but we couldn't make it go away. And so we decided that was something different from the Landau picture. And we published that in this paper here. And soon after that paper appeared, several people read the paper and told me, oh, you have to read this paper by Ed Lorenz, which we'd never heard of. And we read the paper about deterministic non-periodic flow. And that's what we said, well, we have deterministic non-periodic flow. And so I wanted to meet Ed and contacted him and asked him if I set up a symposium at the next American Physical Society meeting in January or February in '76, would he come and be the principal speaker? And he agreed to do that. So he came, and the symposium was first day of the meeting, and on the evening before, Ed and I and the 3 speakers went and had a very nice dinner at Café des Artistes, which is not so far away from the Hilton Hotel on 6th Avenue. And as we came out of the restaurant, we noticed it's snowing. Well, that night, it snowed all night, snowed 18 inches, a half meter of snow. And at 8:30 a.m., the symposium began right on time with Ed as the first speaker, and I introduced him. I wouldn't say there was loud applause. It was a large ballroom. 4 people were present in the audience. Okay. So that was how I first knew Ed Lorenz, and then met him in the next 2 decades particularly. There were many conferences on chaos and bifurcations, and he and I would often meet at these conferences. So the next thing I decided to do in my lab was to study a simpler system than a fluid, something which you have something described by ordinary differential equations rather than partial differential equations. So we have here a tank, a reservoir, like a chemical stirred tank reactor in industry. You feed in the chemicals and it's well stirred, so it's homogeneous in the concentrations. There's no spatial variation to a good approximation. And you vary the concentration of one of the feeds in our experiment, vary it slightly, and you look for the change in the state of the reactor. And we found we could go to a periodic state from a time-independent state, and then we could get, actually we saw period doubling leading to non-periodic behavior. And here are some of the this is a time series that looks, it's oscillatory, but it's not periodic. You can see that the amplitudes are varying all over. So to analyze that, we constructed maps and strange attractors. So here on the horizontal axis, we have the bromide ion concentration at time t, and in the vertical axis, the bromide ion concentration at some later time shifted by time tau later. So a single measurement and its time delay give you a point in this 2-dimensional space. And you will get, as you'll see, trajectories around this. And then to look and see if we could construct a lower dimensional representational, a map, a 1-dimensional map, we looked at the value of xn, this parameter here, when the trajectory, the orbit, crosses this axis. And look at successive values and plot x2 versus x1, and so forth. So this shows the orbits in this 2-dimensional reconstruction. So there you have the first point on the map. And there's the second point. So that's x3, x2. And then you get the next point, and so forth. So you get a sequence of points in this 1-dimensional map. And the question is this a scatter plot, or is there some simple relationship between successive values of xn? There's jitter in the movie because it's a 16-millimeter movie, and it's old. And when it's made off of an oscilloscope, and then we got this used Army Air Force camera to make the movie. So we didn't have an iPhone. So, okay. And the interesting thing was really amazing to us at the time was you get a smooth curve with a quadratic maximum, and it fills out. This is some subset of the data, but you fill out a smooth curve. So xn gives you xn plus 1. We had in mind the title of Ed Lorenz's paper, Deterministic Non-Periodic Flow. It's clearly non-periodic, but it's deterministic. It's determined by this simple map here. Okay, so that's a attractor on the left, or strange or chaotic attractor, and you have that the map determines successive values of x sub n. Now, in this plot here, you see that the orbits along this point all form along a line. And it's hard to distinguish what's going on. And this is with a particular choice for the time delay tau here, this tau. And how do you choose the tau? We didn't know. We worried about that for several years. How do you make the optimal choice of tau, the time delay in this phase space portrait reconstruction? And finally, I had a student Andrew Fraser, who was supposed to be doing a turbulence experiment, but on the side, he started reading about information theory, Shannon's information theory, and he wrote a thesis on application of Shannon's information theory to make the optimal choice of the time delay tau. The people had been arguing the best choice was a minimum in the autocorrelation of the velocity time series, and that gave you this value right here of tau. But here, this is the kind of attractor that we had already obtained. But if you make this minimum in the information, take that value of the tau, the mutual information here, and construct the attractor, it looks like this. The orbits are spread out, and you can obtain accuracy, with much better accuracy, information about the dynamics. So this paper is 5 minutes? Ooh, okay. All right. I can see. Well, so we constructed phase space attractors for the Taylor-Couette system, and here's the case where you have two frequencies. You have flow on an attractor, say in 3 or 4 dimensions, but it's on the surface of a donut surface. And now you intersect it with a Poincare section, and you get this smooth cross-section of the torus. And if you go higher in Reynolds number, then you can see the torus starts to wrinkle. And so that's the onset of chaotic behavior. And in fact, going back to the idea of Landau, that turbulence is described by minute frequencies, a recent paper now has followed a lot of literature talking about characterization of turbulence in terms of a dense set of unstable periodic orbits. And they've shown how the unstable orbits in a turbulent attractor can be identified. Well, we measured the rate of expansion of nearby points. These points are pretty sparse and pretty noisy, kind of embarrassing at this point. And we measured the dimension of the attractor, and we applied it now in whatever minute I have left. We've applied these ideas to many geophysical systems and problems. One problem we looked at was the ozone hole. This colors represent the concentration of ozone in the winter, the Antarctic winter. You have the polar night jet around the pole here, South Pole, and the concentration of ozone is pretty high at middle latitudes compared to the value of the depleted ozone region over the hole. And you notice this very sharp boundary between the depleted region inside the polar night jet and the equatorial concentrations. So we constructed an experiment with a rotating tank, a beta plane on the bottom, and strong forcing, so it had strong turbulent, quasi-geostrophic turbulence here. This was at lower forcing where it was not so turbulent, but we could make it very turbulent. And you see the Rossby waves here in the particle streaks, and we wondered what would happen if we poured dye out here, like the high ozone concentration at the middle latitudes. If we poured dye out here, would it just go across these waves into the center? So we poured dye, and there was a barrier, a very strong barrier here that prevented the dye from crossing over. And this is an example. This is a quasi-two-dimensional flow, so the analysis of the KAM theory applies. You have an invariant curve. The invariant curve has actually started to break here, but it's still pretty strong. If you go a little lower, you have a well-defined invariant curve. Another problem am I out? I'm out of time. Okay. Well, this is turbulent, quasi-geostrophic turbulence. And here you can see a vortex in the bottom, another vortex, and they merge. And these data were analyzed using some of the dynamical systems methods that were developed by George Haller, who was here at MIT in the time when he developed these methods, and now used by many people. You can see, now this is the Lyapunov exponent field, and these are maximizing curves. So I'll just go to the last slide and quit just to say we're still doing experiments on geophysical flows. This is addressing the question in the laboratory of the boluses that form when internal gravity waves go up a continental slope, incident on a continental slope. And this is actual data from Michael Alshaus experiment that was done in Texas, and now he's here, and he's an assistant professor at Northeastern. And you can see a bolus is formed here, which traps material. And the question is, how much in the open ocean where you have just internal waves, there's no transport of material. But here is trapping of material, carrying it up the continental slope all over the world's oceans, but how much is carried up remains unknown. And here's the corresponding simulation, direct numerical simulation. Okay, with that, I'll stop.